Welcome viewers. In this video we'll see the magnetic potential. There are two types available: scalar magnetic potential and vector magnetic potential. First we'll see the scalar magnetic potential. It is denoted by U. Scalar magnetic potential by the symbol is U. So we know that the E equal to minus del V. The relation between E and V, electric field intensity and potential, is E equal to minus del V. The del is nothing but the partial differentiation x, y, z. If it is rectangular coordinate, x, y, z. Similarly, for magnetic potential is given by H equal to minus del U. Here E is replaced by H, V is replaced by U, right? So if we consider this is for electric field, if it, in case of magnetic field, the same thing is given as H equal to minus del U. Now take curl on both sides. While taking curl, what will happen? Curl H equal to minus curl of del U, right? The curl H equal to minus curl of del U. That is nothing but curl H equal to minus curl. This del U is nothing but gradient U. The del U can be replaced by gradient U. But we know that curl H equal to 0. Curl of H equal to 0. But according to Ampere's law, curl of H equal to J, current density. Right? So the normal derivation, normal expression, curl of H equal to 0, but based on the Ampere's law, the curl of H equal to J. Right? These two are not matching together. So from the above relation, the Maxwell's concluded that the concept of scalar magnetic potential is applicable only for magnetic field produced by permanent magnets, right? So the scalar magnetic potential is applicable only permanent magnets, not a electromagnet, right? So the Maxwell's concluded that these relations are applicable only for permanent magnet, not a electromagnet. So this concept cannot be applied to the field produced by steady current. That is not possible to apply for the permanent magnet. Can be applied, not a electromagnet. Cannot applied for electromagnet produced by steady current. So from that, what we can conclude? We know that integral E dot EL equal to V. Similarly, integral H dot equal to U, the scalar magnetic potential, right? But according to Ampere's law, integral H dot DL equal to I, right? So based on this, integral E dot DL equal to V means H dot DL equal to U. But Ampere's law gives H dot DL equal to I. So by comparing these two, these sides are equal, integral H dot dl. So these two expression in these two sides also equal. So that U equal to I. That is scalar magnetic potential is equal to current, right? So we can represent scalar magnetic potential is nothing but a current. So that is given here. The unit of scalar magnetic potential is amperes, right? So we conclude that U equal to I. The unit is amperes. Now we'll see the vector magnetic potential. So vector magnetic potential is denoted by the term A. What is vector magnetic potential? The dA. The A is the magnetic potential. dA means magnetic potential due to small length L. L is the length, small length dl. So due to that, the magnetic potential, vector magnetic potential become dA. So that is, so the dA is the magnetic field potential due to the current element IDL. Current element is nothing but I into dl. That already you know that. So due to this current element, the magnetic field intensity is dA. So this dA is proportional to IDL and inversely proportional to distance r. The distance between the IDL and point P is r, right? So this dA is directly proportional to ideal vector and inversely proportional to r, distance between the point and current element. So while equating, we introduce one constant, that is mu by 4 pi ideal divided by r. So the dA can be expressed as mu by 4 pi ideal by r. So this dA is the magnetic potential, vector magnetic potential only due to small element ideal. So by integrating on both the side, we will get the total vector magnetic field. Now we can refer this diagram. So this is the current element I. Here this is the conductor. The current is flowing through this conductor. Here n number of current elements available. We consider one current element ideal. We need to find what is the magnetic vector magnetic potential at this point P, which is at a distance r meter. Right? So due to the small current element dl, we represented as magnetic potential as vector magnetic potential as dA. Right? So this is the conductor available. The current is flowing through the conductor. Magnetic field is produced. This conductor is assumed to be having so many current elements. We consider only one current element. The magnetic potential due to this current element at point P is dA. This point P is located at a distance r meter. So the magnetic field intensity magnetic potential due to entire conductor can be obtained by integration. So integral, this expression is available. By integrating this, we will get the total vector magnetic potential. So integral dA equal to integral mu divided by 4 pi ideal vector by r vector. So integral dA is nothing but A, that is equal to mu by 4 pi, integral mu by 4 pi ideal vector divided by r. Now for the simplification, multiply and divide with the term area A. Right? We are going to multiply and divide by the term A. So what will happen? So A vector equal to integral mu divided by 4 pi ideal vector divided by r into A divided by A. So the originality will not affect. Area, the term area, A by A. So it is rewritten as A vector equal to mu by 4 pi is constant, that is taken outside. Integral I by A, we are combining these two parameters, I by A into dl divided by r. Right? So this I divided by A is written here, dl A written here, and R is written here. What is I by A? Current by area, that is nothing but current density. What is A into del? Area into length, that is nothing but volume. Right? I by A is nothing but the current density. Current per unit area is nothing but current density. Area into length is nothing but volume. So that A vector, the vector magnetic potential equal to mu divided by 4 pi integral J current density, J dot dV volume divided by R. So this is the final expression for vector magnetic potential. So in this video we discuss about the magnetic potential, the two types, scalar magnetic potential and vector magnetic potential. Thank you. Welcome viewers. In this video we will see the force between two current carrying conductors, force between current loop, and torque on the closed circuit. These three derivations we will see today. So the first one is the force between two current carrying conductors. There are two current carrying conductors available. In between, what is the force is available? Now consider this diagram. So this is the conductor A, this is conductor B. There are two conductors available, conductor A and conductor B. The current flowing through the conductor A is I1, current flowing through the conductor B is I2, I1 and I2. In order to apply Ampere's law, we construct the current loop covering both conductor A and conductor B. Only one current loop is available here. Two conductors are there. Commonly we constructed one current loop. The diameter is d meters. The length of the conductor is L meter. So we have two conductors A and B. The current flowing is I1 and I2. The circular current loop is available covering conductor A and B. The diameter is D and the length is L meter. Right, so that is given here. Consider two current carrying conductors A and B with current I1 and I2 as shown in the diagram. The distance between the conductor is D meters. The loop is formed to cover both the conductors. Now we'll see what is the magnetic field intensity due to conductor A. First we'll consider conductor A. What is the magnetic field intensity due to infinite current carrying conductor? That is H equal to I1 divided by 2 pi d based on the Ampere's law. Integral H dot dl equal to I. From that H equal to I1, because conductor A it is I1. Conductor A, the I1 current is flowing. I1 divided by 2 pi d. Then what is magnetic field intensity? Magnetic flux density? B equal to mu H. The relation is available. B equal to mu H. So the magnetic flux density B equal to mu into the H. H is nothing but I1 divided by 2 pi d. So B equal to mu I divided by 2 pi d. So this is referring the conductor A. Magnetic flux density of conductor A is nothing but mu I1 divided by 2 pi d. Then we'll see what is the force between the conductors. So due to conductor A, the force is developed on conductor B. The force experienced by the conductor B due to the magnetic field produced by conductor A. Right? We already found the expression for B for the conductor A. Now the force is experienced by conductor B due to magnetic field intensity of conductor A. What is the general formula? F equal to BIL. That is the general formula. Magnetic flux density, current and length. Here BI2, because of conductor B it is given as I2. B into I2 into L. This B already we calculated. The magnetic flux density due to conductor A, that is mu I1 divided by 2 pi d into I2 into L. Right? So this B is replaced as mu I1 divided by 2 pi d. So what is final expression? Force between the current carrying conductors mu I1 I2 L divided by 2 pi d. So this force between the conductor depends upon current in the conductor A, current in the conductor B, length of the conductor and diameter of the closed loop, circular loop. These parameters will decide the force between the conductors, right? So this is the force between two different conductors having only one circular current loop. Now we'll go to the force between the current loop, two different current loops, two different conductors with two different current loop. The second one we'll see force between the current loops, right? You see here, see, refer this diagram. So this is one current loop, this is another current loop. Here one conductor is there, here another conductor is available. So in the previous derivation, two conductors with only one current loop is formed, but in this derivation, two current loop is formed for two different conductors. So this is conductor A, the current flowing is IA. For that we consider one circular loop, the radius is A meter. This is conductor B, the current flowing is IB. Here we construct another circular current loop with radius B. The center to center distance between this current loop is X meter, right? So the conductor A, current is IA, the circular current loop radius is A, small a. Conductor B, the current carrying by the conductor B is IB, the radius of circular loop is small b. The center to center distance between the current loop is X meter, right? So that is given here. Let us consider two parallel coaxially placed circular loop of radius A and B, right? The centers are separated by X meters. The current in the coil is IA and IB, right? So due to two different current loop, we will find what is the mutual inductance between the current loop. Mutual inductance M equal to mu divided by 4 pi double integral dl1 dl2 divided by R. So this is the formula for mutual inductance between the current loop. Right. What is here? The double integral is available. That is integral dl1 and integral dl2. What is integral dl1? Integral dl1 is nothing but L1. L1 is the length. Length is nothing but circumference. The circumference 2 pi a. Circumference of this circular current loop. That is circumference of this circular current loop. Similarly, circumference of this current loop. Right. So the dl1 equal to 2 pi a. Similarly, dl2 is L2. L2 is nothing but circumference of the second loop, 2 pi b. Here r we consider as x. Distance between the center to center distance between the circular current loop is x. Now we can replace integral dl with 2 pi a, integral dl2 with 2 pi b, r with x in this expression. So m equal to mu by 4 pi, integral dl1 is 2 pi a, integral dl2 is 2 pi b, and r is x, right? This dl1, dl2 and r is replaced here, right? So after simplification, what we got? This 2 pi available here, 4 pi available, so 2. These 2 and these 2 got cancelled. So finally what we have? This mu pi a b by x, that is pi mu a b divided by x, right? The mutual inductance between these two conductors. Now from that we can find the force between the current loop. What is the force between the current loop? The force between two coil with current IA and IB is given as F equal to IA IB dm by dx. So this is the current in the first coil, current in the second coil. D by dx means differentiation of mutual inductance with respect to x. Distance, center to center distance between the coil x, right? We need to differentiate the expression mutual inductance with respect to x. Now we'll substitute the value of m here. IA IB d by dx of the mutual inductance what we calculated as pi mu AB divided by x, right? So this m is replaced by this expression. So this IA IB pi mu A is constant. Only what we have? D by dx of 1 by x. Only this 1 by x. We need to differentiate only 1 by x. Pi mu AB is constant. What is differentiation of 1 by x? Minus 1 by x square. So IA IB mu pi AB into differentiation of 1 by x is minus 1 by x square. So finally what we got? Force between the current loop, right, is minus IA IB mu pi AB divided by x square. So the force is depends upon current in the first conductor, current in the second conductor, right, radius of the first loop, radius of the second loop, and square of the distance between the center to center distance between the current loop, right? So this is the final expression. Now we'll see the torque on the closed circuit. Now we'll see torque on this closed circuit. Refer this diagram. So this we have one conductor AB, BC, CD and DA. Right? We consider this is one conductor AB. This is another conductor CD. This is another conductor DA and AB. One closed loop. The conductors are placed in a closed loop. The length is L meter, the width is W. This is x-axis and y-axis. This point P and Q is exactly placed at the midpoint. The point P is the midpoint. Now we need to see what is the force between this conductor and what is the torque between this conductor. Finally, what is the torque developed? Right? It is a rotating coil. If it is rotating coil, the torque will be produced. Right? So we have four conductors AB, BC, CD and DA. The length is L, width is W. The point P is located exactly at the half of the length of the conductor. We know that the torque, the force on this BC and DA is 0 due to normal. Only the force available in AB and CD. Right? We will see this one by one. The conductor AB is placed in the field with uniform distribution. that is conductor AB is placed in the electric field. Similarly, CD also placed. First we consider AB, then we can go for CD. That's why only given AB. Then what is the another description? The P is the midpoint of AB, where AB has the length L. Right? The point P is located at the midpoint. The current flow from A to B. In this diagram, the current is flowing from A to B. In case of C, it is going from C to D. So one current is going upward, this current is going downward. The field is directed from parallel to x-axis. Then the force on the each element of dl of AB is. The L is the total length, dl means small length in the conductor AB. What is the force? I dl into B. The general formula is available, BIL. Current length into B. So that I into BL, we can write like this. So the total force on conductor. Now only consider AB. What is the total force on conductor? AB is I into B into DL. In case of CD, it is minus I into B into DL. Right? So which means that the magnitude of force is IBL. Both are same, only the direction is negative. The direction along y-axis is negative. Right? So both are, the magnitudes are both are same. IBL, here also IBL. This negative sign indicates the force on the y-axis is negative. If we consider the loop ABCDA with the dimension L into W, the total torque on this loop is given as a torque equal to 2 into torque on each side. We consider AB and CD. Right? So the total torque is nothing but 2 times of torque on each side. What is the formula for torque? Force into distance between the axis of rotation. That is the general formula. Torque equal to F into distance. Right? So the 2 times, because we consider on both the side. So 2 into the force we already calculated, IBL. For both AB and CD is IBL. Only the negative sign is there. That indicates it is going in negative direction. The distance from the axis of rotation is W by 2. Because W is the width, the point P is located exactly at the half. So that's W by 2. So these two got cancelled. So finally what we got? IBLW. Right? That can be written as I into WL into B. What is W into L? Width into length. That is nothing but area. Right? So the WL can be replaced. WL is nothing but A. Right? So that torque equal to I into A into B. Current, area and magnetic flux density. The torque is defined by these 3 parameters. So in this video we discuss about the force between 2 conductors and force between 2 current loop and torque on the closed circuit. Right? Thank you.